Hello everyone, my name is Rahatara. I am a PhD candidate at the University of Ottawa, and today I will be presenting our paper entitled as TextureMeDefect LLM-based synthetic railway defect texture on mobile devices. This research stems from the growing need for innovative portable solution in industrial defect visualization. Now, synthetic texture generation is already transforming the fields like gaming, art, and design. However, its potential in industrial application, particularly for visualizing complex defect patterns, remained unexplored. Imagine being able to quickly and easily generate realistic textures of cracks, corrosion, or other defects on a variety of materials. This capability can incredibly helpful for a wide range of purposes from training and simulation to product development as well as quality control. Today's consumer-grade devices like a smartphone and tablets offer incredible portability and interactive features, which making them ideal for industrial application where instant decision-making is required and needed to be used in remote areas. Consider a railway inspector working in the field and they can use their smartphone to take a picture of a rail wheel and with a mobile application instantly generate realistic textures on the image. Such app will help them in on-site assessment and decision making. However, when it comes to portable mobile devices, factors like resource constraints and high computational demand to pre-process visual information poses extreme challenges to fully leverage the benefit of such tool on consumer-grade devices. On top, we found in the literature that traditional methods for texture generation, such as stochastic algorithms and procedural modeling, fall short when it comes to creating the fine-grained domain-specific details required for realistic defect texture generation. For example, stochastic algorithms are efficient for general patterns, but it struggles to capture the subtle variation and complexities of real-world defects. On the other hand, procedural modeling is capable of producing detailed texture, but it is computationally expensive, which makes it unsuitable for deploying on mobile devices. And these devices often have limited memory or power consumption ability. Advanced AI-based tools like STXL, DALI 3, and Instruct Pix2Pix, they are proven as powerful AI models for artistic and creative application. But if we want to use that for defect texture generation, it lacks precision needed for industrial defect texture generation. And this model often generate hallucinated or irrelevant textures, which is not useful for the target consumers. Now, the limitations of these existing approaches create significant gaps that hinder the widespread adoption of synthetic defect texture generation tools in consumer electronics. High computational demands make many current methods unsuitable for resource-constrained devices, and poor usability further limits their accessibility to a wider audience. Now, to overcome these gaps identified in the literature, we focus on three key objectives and requirements. First, we want to introduce a light AI inferencing engine that enables fast and efficient texture generation on resource-constrained devices. We also need to achieve the domain-specific adaptation, ensuring the tool is specifically generating and visualizing the unique characteristics of defect textures, and which also aligned with the requirement for a pre-trained LLM like ChatGPT, well, this should be fine-tuned with the descriptive visual characteristics of the particular defects. Finally, we need to create an intuitive user interface that is easy to use on mobile devices and offer a mobile-friendly human AI interactions. But still, there is a big challenge remaining on the way. For industrial applications where defect is a safety hazard but not very frequently occurring, event like where we will get enough samples to customize the LLM to capture fine-grained details of various textures. Now, to address these requirements, in this research, we propose TextureMeDefect, which is a cross-platform tool that leverages the power of LLM-based AI inference to generate synthetic defect textures directly on users' mobile devices. Now, let's see how the system architecture of this tool works. As this slide illustrates, TextureMeDefect system architecture, it has two main components: the multimodal user interaction interface MUI and the AI inference engine. Let's take a closer look at each. The MUI here serves as the user-friendly front end, enabling seamless interaction with the AI inferencing engine here. Users can utilize their smartphone or tablets to input data through gestures, touch, or keyboard. And these components target minimizing the poor usability problem by providing a way to the user to interact with the next component, which is the AI inferencing engine, by letting user interact with the multimodal input and output. Now, the AI inferencing engine here is the heart of TextureMeDefect tool, where the LLM-based AI processes all user inputs and generate defect texture. But let's break down how it's achieving the requirements step by step. To resolve the root problem for domain-specific customization of LLM, we proposed an algorithm associated with synthetic dataset generation. From a real-world capture image, a visual captioning LLM like GPT-4 generate multiple versions of the defect textures, including specific characteristics supposed to be in the visual description. Each of these align with concatenated with a system message instruction, which ultimately produce a custom visual instruct dataset. And this dataset is specifically designed to capture the fine-grained details of variation found in real-world railway defect. Then the dataset is used to fine-tune a base LLM like GPT-3, and here to textually generate the visual texture description of the defect. The dataset we produce is available on open source under our open source project on GitHub. You can access them through the link we provided in the paper. When users send the request in a form of a prompt that to the like AI LLM, here they want to generate a certain defect characteristics, and we inject another approach which is called virtual prompt injection to make sure that the prompt is in context, so that a specific defect texture that we're targeting to address on the image is reflected. So when the prompt is passed after in a refined format, the text to image generation or image plus text to image generation model produce the relevant and real world specific output. Now, as a tool, TextureMeDefect handle multiple scenarios for defect texture generation, and the model can be based on multiple model. For example, for in-paint texture generation, we used here the Instruct Pix2Pix model as a base model, while for the text to defect generation, we used SDXL2 as the base model, and the models are selected dynamically based on the user selection on the MUI, and the figure here shows how the generated defect texture was applied to a given 3D model of a heavy freight for advanced visualization. But does our proposed TextureMeDefect tool still fulfill the objective we target? To understand that, we performed a couple of evaluations here. The TextureMeDefect consistently outperformed the existing methods in generating highly relevant and realistic defect texture, especially for the third scenario where we passed an image and we wanted to see how the tiered condition will look on this image. You can see here how SDXL or DELI2 were hallucinating and produced irrelevant output, while our proposed tool could specifically capture the context and produce more realistic output. Also, it's ought to mention that the fine-tuning process for TextureMeDefect tool only required 450 examples, demonstrating its efficiency in learning from limited data, and which is really important to fulfill the requirements of lightweight AI model. We are not doing here any heavy training, exhausting a lot of computational resources. To talk about the latency, which is basically a metric presenting the time needed to generate the response, you can observe that the TextureMeDefect excelled in terms of latency, generating textures significantly faster than other models across various scenarios. And especially for the first scenario, our tool achieved the lowest latency across all scenarios. For example, in the predefined prompt, it process textures in just 15 to 20 seconds on iOS compared to 28 seconds for DALI 3. Even in complex in-painting tasks, our latency remains significantly lower. Further showcasing its efficiency, the fine-tuned LLM in TextureMeDefect use significantly fewer tokens than the base models, and this lead to faster processing and lower cost. Token is the atomic part of generated text by the LLM, and it has significant impact on both speed and cost. Also, the concise token is beneficial when it is passed as prompt to diffusion models to avoid hallucinations, so that your text to image or any image generation model doesn't deal with extra information that can cause or that can make the model confused. Now, our fine-tuned model, as it reduced the token generation by up to 50%, enhancing the efficiency. From an estimate of the cost based on the token and the processing time, we can clearly observe here that the scenario 1 had the lowest processing cost. However, like for the scenario 3, we had the cost increased moderately, and in this scenario we had like a higher token uses, and that need to be actually improved, and which is one of the limitations of this research work. We also compared the ACUS across like Android and iOS platforms and all for specific questions. So as we see here, for scenario 1, it demonstrated highest usability with the scores averaging 4.5 to 5 for the questions, and for scenario 2, it allowed challenges in prompt clarity, highlighting the areas for interface improvement. For scenario 3, we found a struck balance. Even though the delay for the getting the response a little bit more, for scenario 3, users were happy with the output quality, so it has struck between a balance excelling the output quality. To conclude, we would like to say that TextureMeDefect is the first LLM-based mobile defect texture generation tool specifically designed for industrial application. Our evaluation demonstrates that the effectiveness can be applied to the real-world scenarios, achieving significant improvements over existing methods. Also, this is a mobile-first approach, aligns perfectly with the evolving demands of on-site and remote operation in various industries. While TextureMeDefect shows great promise, there are some limitations to consider and opportunities for future development. Moving forward, we aim to explore the hardware accelerators like language processor units. We want to refine the user interfaces and enhance the scalability for the broader industrial applications. Thank you for your time. We believe that TextureMeDefect has the potential to transform the way we approach defect analysis and visualization as a consumer electronics application. And we invite you to explore this exciting technology and join us in shaping the future of the industrial inspection. If you have any questions, please feel free to reach me out. If you want to collaborate, you can also try to contact our lab, and feel free to watch the demos and promos and using the code and dataset associated with this paper.